Good morning. Today we are going to see shearing stresses in beams. So far we have seen about how to calculate the shear force and bending moment values for a given beam subjected to different types of loading, say concentrated load, uniformly distributed load or uniformly varying load, and also the couple. And we have seen that the bending stresses calculation and its distribution also, and we have learned that bending stresses are produced due to bending moments. Now, the shearing stresses in beams that are produced due to shear forces that are set up along the span of the beam due to the external load application. Say the external load may be like point load, UDL, UVL. So now let us see how to determine the shearing stress or shear stress values when a beam is subjected to different types of loadings, and let the beam have or beam take different cross sections like a rectangle, circular, I section or a channel section, T section, whatever it is. Okay, the procedure is same. Okay, so I'm not going to derive any expression. I'm going to take the final formula. With that formula we will see how to solve the problems. Okay, how to solve the numericals. So this is the expression tau is equal to FA y bar divided by I into B. I into B. Now for example, so let me draw a cross section. Let me draw one cross section. Okay, one for example rectangle cross section. Okay, suppose if this is my cross section of the beam, cross section of the beam, and this is my neutral axis. This is my neutral axis. So now I want to find the bending stress. Now I want to find the bending stress. For example, I want to find the bending stress here. I want to find the bending stress here. I want to find the bending stress here, or anywhere above the neutral axis. We call this as a neutral axis. We call this as a neutral axis. Now tau is equal to F A y bar by I into B. What is F? F is nothing but maximum shear force. Maximum shear force. Now for example, we have seen in the bending stress, I have given one tabular column where it shows, for example, for different types of beams subjected to load, we have seen the maximum bending moment formula. Let us take, for example, simply supported beam subjected to point to the middle means WL by 4, and simply supported beam subjected to an eccentric point to WAB by L. Simply supported beam subjected to UDL means WL square by 8. Cantilever beam subjected to point load the tip W into L. Cantilever beam subjected to UDL or the entire span means WL square by 2. So these are the direct formulas that are available to calculate or determine the maximum bending moment. And also, if more than one type of load is given on a beam, like a point load or a UDL means, we try to locate a zero shear force location. Then about that point, we take a moment to determine the maximum value of bending moment. And that M value is substituted in the formula M by I is equal to sigma B by Y to determine the maximum bending stress. So here, we're looking for calculating the shear stress in beams. So the F refers to the maximum shear force. So whenever you get a beam, we should try to calculate the maximum shear force acting on that beam by plotting the shear force diagram if more than one type of load is given. For example, simply supported beam subjected to point load the middle means W by 2 is the maximum shear force. Like this, you can remember it. Now, simply supported beam with UDL means WL by 2. Then cantilever beam subjected to point load the tip W means W is the maximum shear force. Then cantilever beam subjected to UDL throughout the span means W into L is the maximum shear force. Or cantilever beam subjected to an eccentric point load means, for example, eccentric point load means a point load acting at different distance from either side of the supports. For example, let us say distance A from the left hand support and distance B from the right hand support. Okay, so if A is greater than B means WA by L is the maximum shear force. So like that, we have to determine the first the maximum shear force, which we need to plug into this formula. Okay. Now, for example, if it is required to find the what you call the shearing stress at any specific point above the neutral axis. For example, now I want to find the shearing stress here. Now I want to find the bending stress here at this point. Okay, at this point. So now what I will do is I will consider this section to find the shearing stress. So I will consider this section above this marked point. Okay, above this marked point. So A is nothing but area of the shaded region. A is nothing but area of the shaded region. Y bar is nothing but. Now for this shaded region, you will have one CG point. So Y bar is nothing but this distance of CG from the shaded portion to the neutral axis. This is nothing but Y bar. This is nothing but Y bar. Then what is I? I is nothing but the area moment of inertia. We know that the rectangle section having width B and depth D, for example, and the area moment of inertia I is nothing but BD cube by 12. Very simple. And B is nothing but width of the beam. B is nothing but width of the beam. So like this, I have shown for a simple section, rectangular section. We'll see for T section, I section, how to take the B values, how to take B values. Okay, because section is not uniform over the depth of the section. Here the section is uniform. Okay, whereas I section is not, section width is not uniform along the depth of the beam. Okay, that we'll see it later. So this is the formula we are going to use. Tau is equal to F A Y bar by I into B. Now for a rectangular section, okay, this is a rectangle section, and this is the neutral axis, B is the width, and D is the depth. Okay, we have marked 2 points at the top A and at the bottom B. And for rectangle section, we have arrived the formula to be tau is equal to F by 2I d square by 4 minus y square. Okay, y is nothing but distance above the neutral axis. Okay, or below the neutral axis, so no problem. Okay, y is nothing but distance from neutral axis, that could be above the neutral axis or below the neutral axis. Okay, I is a moment of inertia like BD cube by 12. So now, if this is my expression to determine the shearing stress for beams, now at A, for example, y is nothing but total depth divided by 2. So total depth is d. So this is nothing but d by 2. At A, y is equal to d by 2. There is shear stress at A. Substitute this y is equal to d by 2 in this expression. You will get d square by 4 minus d square by 4, which is nothing but a 0. So shear stress at A is 0. So we have marked a point. Tau VA is equal to 0. Then at B, y is equal to again d by 2. Okay, even if you take minus d by 2, also nothing wrong in that, because we are going to square it. So again d square by 4 minus d square by 4, tau B, shear stress at B is 0. We have marked a point here. So at the neutral axis where y is 0, so you get fd square by for I think it's fd square by 8i, right? Fd square by 8i. So here by mistake I written 2i, it's 8i. So here f by 2i into d square by 4. F by 2i into d square by 4. Okay, d square by 4. So I is nothing but bd cube by 12. So we get from this d square will get cancelled, and 12 by 4 is 3, so 3 by 2 into f by bd. F is the shear force, b into d is nothing but area of the rectangle section, length into breadth. Now here in this case, width into depth or breadth into depth, whatever it is. So tau max is equal to, I can call this shear force by area as average shear stress. I can call this as average shear stress. Tau average for a rectangle section is given by F by BD. So F by BD, tau average is nothing but F by BD for a rectangular section. So maximum shear stress is equal to 3 by 2 times F by BD. That is, maximum shear stress is equal to 1.5 times the average shear stress. So this is a standard formula for a rectangle section to determine the, or to give the relationship between the maximum shear stress and average shear stress. Now you just mark a point here, tau max. This is a tau max. Just mark a point. If you look at the shear stress expression here, y square we are getting. So the nature of the shear stress diagram must be a parabola. So just connect A to tau max and tau max to tau B. You just draw a parabola. This is the shear stress distribution for a rectangular section. So we have seen for the same rectangular section bending stress distribution also we have seen. For example, same rectangular section how we have drawn. This is my rectangle section. Now this is my neutral axis. How we have seen this. Now this is my, of course, the depth we are trying to plot it. Okay. Now we are just trying to draw the bending stress. Bending stress distribution is always linear. Okay, linear. So like this it went. Then from here it should come like this, and it should go like this, right? So here the bending stress would be zero. Okay, so here the bending stress is zero. Okay, because already I told you bending stress at the neutral axis is zero. Okay, this is our neutral axis. Whereas bending stress is shearing stress is maximum at the neutral axis. So both are like opposite. So bending stress is always zero at the neutral axis, whereas shearing stress is maximum at the neutral axis. Okay, like how we get in shear force and bending moment diagram, shear force is zero where bending moment is maximum, and bending moment is zero where shear force is maximum, right? So you can see here is a linear variation, this is a parabolic variation. Okay, so here if the beam is a simply supported beam means the bending stress, the nature of the bending stress would be compressive above the neutral axis, and below it could be tensile in nature. Okay. Now, when you go to this circular section, okay, circular section, okay, let us take a beam of a circular section of radius r. Okay, radius r. This is our neutral axis. I have taken 2 points A and B, top point A and bottom point B. Okay, this is the expression for circular section. Tau is equal to f by 3I into r square minus y square. So y is nothing but distance above or below the neutral axis. So we can say distance from neutral axis. So at A from the neutral axis y is r. Even at B also y is equal to r. You should not take minus r. Okay. So radius will never be negative. So at A and B y is nothing but r. If you just substitute this y is equal to r in this expression, I get the shear stress at A and B to be zero. So here tau A is zero, tau B is zero. Now at the neutral axis where the y is zero, the maximum shear stress where it acts, substitute that y is equal to 0 in this expression. So fr square by 3i, fr square by 3i. So I is nothing but pi d power 4 by 64. Now here I have written in terms of r, where I is equal to pi r power 4 by 4. Okay, so r square will just cancel. We get 4 by 3 f by pi r square, where pi r square is the cross-sectional area of a circular section. So shear force by this area, I can call this F by pi r square as average shear stress for a circular section. So the maximum shear stress is 4 by 3 times the average shear stress for a circular section. Again, y square we're getting. So the nature of the shear stress distribution or shear stress diagram would be a parabola. Simply connect tau A, tau max and tau B by means of a parabola. So let us do a simple problem on this. I've taken a beam, okay, 100 millimeter wide rectangle section, 150 millimeter deep, which is subjected to a shear force of 30 kilonewton. We have to determine the average shear stress and the maximum shear stress. So write down the given data. B is equal to 100 millimeter and D is equal to 150 millimeter, and the shear force given in the problem 30 kilonewton. We have to find tau average and tau max. Tau average F by BD. So if you just substitute the values, substitute 30 kilonewton in Newton, so you get tau average to be 2 Newton per mm square, and tau max is 3 by 2 or 1.5 times tau average, which is coming out to be 3 Newton per mm square. Sometimes if they ask you to find the, for example, bending stress at a distance of, now this depth is 150, right? So this depth is, so this depth is 150, okay? So this is our neutral axis. This is our neutral axis. Now, if they ask you to calculate the what to say the shear stress at a distance of 25 millimeter, okay, 25 millimeter above the neutral axis. Now here I want to find out. That is, let us say like tau 25. You've got tau average, tau max, and tau here it would be 0, and here it would be 0, right? You've got the maximum shear stress values also. Now how to find this? We have got one formula in the beginning. I have given the one formula, F by uh, F by 2I d square by 4, d square by 4 minus y square. Okay, so determine the shear stress. Now only find the tau 25. So tau 25, for example. So this 25, in place of y, you have to substitute 25. So 25 square. D is nothing but 150 square. I is nothing but BDQ by 12. F is nothing but, for example, 30,000 Newton. Now determine the shear stress at a distance of 25 millimeter above the neutral axis. Above the neutral axis. Sometimes they can give 25 millimeter below the top of the beam. Okay, below the top of the beam. And in that case, total depth is 150, right? So half of this will be 75. So 75 minus 25 would be your y value. That is 50 would be your y value. So please remember. Okay. Now next problem, a timber beam of a rectangular section is simply supported at the ends and carries a point load at the center of the beam. The maximum bending stress is 12 Newton per millimeter square and the maximum shearing stress is 1 Newton per millimeter square. Find the ratio of the span to the depth. Span is nothing but length. Okay, length to the depth. Let us say depth, small letter d. Okay, depth of the section. So we have to find the ratio L by d. Okay, length divided by depth. So this is the beam, simply supported beam subjected to point at the middle W. Okay, we know that we can find the support reactions without writing the static equilibrium equations. Now the load is exactly acting at the middle. So we are having two supports. So RA and RB would be W by 2, W by 2, W by 2. This is the cross section of the beam, rectangle section. Width is B and depth is D. Bending is 12 Newton per mm square and the shear stress is 1 Newton per mm square. We have to find L by D. Now we know from bending stress M is equal to I by Y into sigma B, where I by Y is nothing but Z section modulus, and Z section modulus for a rectangle section is BD square by 6. This we have seen already. And we know the relationship between the tau max and tau average for the rectangle section, which is nothing but 3 by 2 or 1.5 times the tau average. Tau average is given by F by BD, F by BD. So for a simply supported beam with point load in the middle, we know the maximum bending moment is given by the formula WL by 4 and the maximum shear force is W by 2. So from the second equation, we get tau max is 1 is equal to 3 by 2 and F is nothing but W by 2 divided by BD. From this we get W by BD is equal to 4 by 3. From the equation 1, from equation 1, M is nothing but WL by 4, BD square by 6 into sigma B is 12. So substitute here W by BD, W by BD, take the BD to the left hand side denominator, W by BD is nothing but 4 by 3 and L and take this D1D to the left hand side denominator. So W by BD into L by D is equal to 8 you will get, okay, is equal to 8, that is 6 2s are 12, 4 due to cross multiplication 8. So W by BD is nothing but 4 by 3. So just by simplification, we get L by D. Span to the depth ratio is nothing but 6. for the given problem. So next problem, if you come to this problem, a simply supported wooden beam of span 1.3 meter, having a cross section 150 millimeter wide and 250 millimeter deep, carries a point load W at the center. The permissible stress or 7 Newton per mm square in bending and 1 Newton per mm square in shearing. Calculate the safe load W. Okay, so this is the same condition as previous. So here 1.3 meter length, 150 millimeter width wide, and 250 millimeter is the depth. This is the bending stress, shearing stress. We have to find the safe load. So as we have seen in the previous problem, m is equal to bd square by 6 into sigma b. M is wl by 4. bd square by 6 into sigma b. Substitute sigma b here, b value, d value, length, find w. So w is coming out to be 33.65 kilonewton. 33.65 kilonewton. I have converted newton to kilonewton. So by considering the bending stress, that is bending stress consideration, you get the w value to be 33.65 kilonewton. And tau max is equal to 3 by 2 times f by bd, that is tau average. F is nothing but w by 2, okay, bd. So from this you get w value to be 50 newton or 50,000 newton or 50 kilonewton. So safe load is minimum of these two values. So minimum of these two is 33.65 kilonewton, which is the answer for this problem. So by considering the bending stress, we get one W value. By considering the shearing stress, we get another W value. Out of these two, we have to choose the minimum value to be the safe load for the given beam. Now let us look at the circular section. Okay, circular section of 100 millimeter dia subjected to a shear force of 5 kilonewton. We have to find the average shear stress and the maximum shear stress. So we know the formula tau max is equal to 4 by 3 tau average. Tau average you can calculate like F by pi r square, which is coming out to be 0.636 Newton per mm square. And if you just multiply this by 4 by 3, you will get 0.848 Newton per mm square, which is the maximum shear stress. Thank you. I will stop with this.